Hello everyone, my name is Weiqi. Today I'm going to share our work, Optimus, accelerating large-scale multimodal LLM training via bubble exploitation. So it is joint work between Harvard, ByteDance, and the USC. So let's start with the background. So we all observe that multimodal large language models are increasingly popular. So many large companies and also startups are focusing on this area. For example, we have a GPT-4o, Gemini, and also Lava from open source community. And they are really good at processing data of different modality, and they can support a wide range of applications. So one example application is that you can upload a picture to a chatbot, and you can ask some question. For example, what is in the box? And let's take a look of the multimodal large language model architecture. So it is usually composed of two parts. So the first part are multiple encoder, and the majority part will be a large language model backbone. Because the multimodality large language model, it needs to process data of different modality. So usually they will have an encoder for each type of data. For example, for the image, there will be an image encoder, while for the audio, there will be a dedicated audio encoder. And after each encoder processes the input data, it will align the feature in the same feature space, while the large language model will going forward to compute the final output. And we observe two unique characteristics of multimodal large language model. The first one is, although it composed of two parts, but still the dominant model size belong to the large language model backbone. For example, we look at the Flamingo model. In total, it has 80 billion of parameters, while 70 billion of the total parameters are from the large language model. The second part is there is a dependency between encoder and LLM backbone. For example, during the forward pass, the encoder needs to first finish generate the feature before the LLM can do in the forward. And in the backwarding pass, vice versa, they have similar dependency. And we look at the current 3D parallel training system for multimodal large language model. We think that they are not very efficient. The key reason is 3D parallel training are originally designed for symmetric transformer model. For example, they are used to train the large language model itself because it is a homogeneous model architecture. So each pipeline is balanced, so it can do a good work. However, if you want to use it to do multimodality large language model training, it requires some adaptation. For example, one common practice is they will place encoder in the first pipeline stage to do the training. However, it will result into pipeline imbalance because now the first pipeline stage is actually doing more work compared with other pipeline stages. So here is the outline of my talk. So first, I will start with our key insights, and the direction we want to go is trying to scheduling encoder computation into the LLM bubble to reduce the end-to-end training time for the multimodality large language model. Secondly, I will look at the key challenges of doing this and also highlight the design decision we made in Optimus paper. So finally, I will cover the evaluation. I will show the performance of Optimus at scale. So let's start with that direction. So our key observation is there are significant GPU idle time in multimodality large language model training. In our internal large-scale training task, we observed that over 48% of GPU cycles were idle. And this bubble attributed to three main causes, which is the 3D parallelism. For example, because of the data parallelism, before the training step, you need to do some data parallel or gather communication. At the end of training step, you need to do reduce scatter communication. Because of this communication, the GPU cannot do any work. They need to wait for the communication to finish before doing the next iteration. Secondly, we have pipeline parallelism dependency. Most notably, during the pipeline warm-up phase and the cool-down phase, the adjacent pipeline stages need to wait for each other before they can start computation. Lastly, we have tensor parallelism, which also do some communication because we need to divide the matrix into multiple GPU and it requires some actual communication to gather the result. And our second observation is based on our production data analysis. The majority of the bubble, around 90%, occur during the LLM forward pass and backward backward pass, which means that like we observe lots of bubble like in multimodality large language model training, and most of the bubble exists like during the LLM part. So our direction here is like, suppose that we can have a smart way, we can schedule the encoder computation into the LLM bubble. For example, like in this training timeline, there is some gray box here, which are the bubble. Suppose we can utilize them to do the encoder computation, so we can improve like the overall like training efficiency. So let's take a look for the Optimus design, which will make bubble exploitation for multimodality large language model training works in practice. So the first challenge we see is like the current 3D parallelism strategy make only a limited number of GPU have both encoder and LLM model states. For example, the 3D parallelism strategy will divide the model as a single pipeline. The strategy we cover about like they will place like, for example, they will place the encoder into the first pipeline stage. So only the first pipeline stage will have both encoder and LLM model states. While for other stages, it will only have LLM model states. However, like holding both states are necessary condition to scheduling encoder computation within LLM bubble. Otherwise, when the GPU has like the idle work, because they don't have like the encoder model states, they cannot like do the computation. So our approach is we're trying to collocate encoder and LLM to every GPU, and we use a separate parallelism strategy. So this picture like shows our idea. So we view the model as two parts. One is encoder, the other is large language model. For each part, we chose its own parallelism plan. For the large language model, there are already lots of work covering how you can find the right parallelism. For the encoder part, you can also like choose their own parallelism. And after you decide like the parallelism strategy, we will allocate like the GPU, we will allocate the model into every GPU. For example, here, the encoder are using a different parallelism strategy compared with LLM. It has two benefits. So first, like after choosing a separate parallelism, all GPU will have both encoder and the large language model states. And the second benefit is encoder can select parallelism plan to optimize its computational efficiency. Traditional like 3D parallelism approach using a same parallelism plan for both encoder and LLM, but encoder, the model architecture itself is inherently different from the LLM. For example, it can have like a smaller hidden size. When you're using like a large tensor parallelism, actually it cannot achieve good computation efficiency. By collocating the encoder and LLM with separate parallelism, you can choose the parallelism plan that suits best like for the encoder. Our second challenge is we have a really complex dependency in MLLM training. So the first dependency is like because the synchronous training, it has an iteration dependency. When we use LLM bubble to do the encoder computation, we can only use the bubble within this training iteration. We cannot utilize the bubble from the next iteration or previous iteration. The second is because we still need to use pipeline parallelism to do encoder and LLM. It has internal dependency because we need to partition it into different pipeline stages. The last one is the most complex one. Because we have two parts, one is encoder and another is LLM. It has a macro batch level dependency between the encoder and LLM. Because like for the forwarding pass, the encoder needs to first finish the calculation before the LLM can move forward. And in the backward pass, LLM needs to first finish the gradient computation before the encoder can continue the compute. So for the Optimus, like our approach is we use a dual stage dependency management. So we break down it like into two parts. So the first part is like local scheduling. The second part is like global ordering. Because we are using different parallelism plan for encoder and LLM, so for the GPU that deploy one LLM pipeline, it can be like a multiple encoder pipeline. So our approach is like we will divide the work into different pipelines. Well, for each pipeline, it will try to schedule its computation within the available LLM bubble. It will satisfy the first two dependencies we covered, the iteration dependency and also the encoder internal dependency. And we have a second stage called global ordering. It will take a look like from the global view. It will check for all the macro batch. It will ensure the macro batch level dependency by comparing the time step between the encoder finish computation and the LLM like start computation. So in the paper, we have a detailed algorithm, which is a greedy algorithm. The key insight is it is an iterative optimization. For each step, we will first do local scheduling, then we'll do global ordering, and we will keep move forward until we cannot find enough variable or it violates the data dependency within the training. Our last challenge is one special type of LLM bubble. They are actually very short. For example, the bubble caused by tensor parallelism, it's less than 1 millisecond. Based on our profiling, it is around 300 microseconds when we profiling to GPT 175 billion transformer layer. So when using this kind of bubble, it is actually hard because our first attempt is we schedule encoder computation into layer granularity, but even one single layer can be longer than 1 millisecond. So our approach is we schedule encoder computation at the kernel level, and we decomposing encoder layer into kernel. For example, if you look at one encoder layer, it can be further decomposed into compute kernels and communication kernel. And here we do a carefully overlapping. When the LLM is doing the communication, we will schedule the encoder computation. When the LLM is doing the computation, we will doing the encoder communication. So in this way, we avoid the TP communication bandwidth conflict when doing the training. So finally, I will cover the evaluation, the performance of Optimus at scale. So here is the overview of our evaluation. So we build a multi-modality large language model with different image encoder size from 5 billion to 22 billion. And we use 2 different sizes of large language model backbone. And our key metric is the iteration training time and the model flops utilization. We conducted our experiments on production training cluster with thousands of NVIDIA GPU. So the baseline we are comparing 2 strong baseline. The first one is Megatron LLM, which has an adaptation of placing encoder into the first pipeline stage to adapt to the MLLM training. The second one is we create a stronger baseline. Basically, we have a dynamic programming algorithm to assign different layers to different stages to ensure they are balanced. And we also compare with FSDP and APA. So in the weak scaling experiment, we scale the model size with the GPU count, evaluating the weak scaling performance of Optimus. So as you can see here, we create a model from less than 100 billion, to 200 billion, and we increase the number of GPU from 64 to 512. And we found that Optimus can achieve a speed up about 22% compared with Megatron LLM and 18% compared with Megatron LLM balance. And for the APA, the SDP, when we evaluate it at a larger scale, it will fail because it doesn't have enough memory to support the training. We also conducted strong scaling experiment. So we picked the 200 billion size model, and we increasing the number of GPU from 1,500 to 3,000 while keeping the same batch size. So the key observation here is we check our MFU utilization. It is actually pretty stable compared with other baseline. They have some drop when you scale it at a large scale. We think the key reason here is when you're doing a large scale training, there will be more bubble. But because of Optimus approach, it can actually utilize more bubble to do the encoder computation. So overall, it can achieve similar SFU. And we also found that we have 20% improvement for the training time. So we have more results in the paper. For example, Optimus performance with multi-encoder MLLM. And also we check its GPU memory usage overhead. And also we have a view for the bubble scheduling efficiency and algorithm runtime. So in summary, Optimus is a distributed MLLM training system that schedules encoder computation into LLM bubble to reduce the end-to-end training time. We conducted our experiment over 3,000 GPU, and we found that it can achieve 20% speed up compared with the state-of-the-art solution. Yeah, that's it. So thank you, and welcome to any questions.